Thank you very much, Jesse. It was a great introduction. Thank you, everyone, for coming to my talk about famous bugs. And thank you for PyGotham for giving me the opportunity to give this talk. I had an idea about this talk for a while now. So my name is Ian Zelikman. I've been doing Python development for about 7 years now. Mostly focused on back-end web services or back-end development. Currently, I work for IBM Watson Health. We do a lot of cool stuff with developing, specifically for me, data pipelines for high-volume data for our main healthcare providers. The reason I wanted to give this talk is I found this area fascinating. As Jesse said, it's interesting to talk about successful projects, about how awesome it is, but I find it very interesting to see how our industry progressed and how we can learn from these famous bugs. And I hope this will inspire you also to learn from your bugs and research other bugs, famous bugs that might be out there. We saw this morning at our keynote some other famous bugs, and we'll dive to some cases here. So I wanted to start to talk a little bit about how we use the word bug. Basically, in the software industry, we describe bug as some unintended consequences, something that cost us for a failure. How it actually originated is currently researchers find the words like bugaboo or bugbear as early indication of the word bug, kind of ancestors to it in early English, and they all used to describe monsters. This is a letter, very small print, written by Thomas Edison at 1878. This is the very first written record we can find for using the word bug to describe some mechanical malfunction. This is the very early written record we can find. We don't know for sure if Thomas Edison himself was the first one to use this word this way, but it was somewhere during that time that it started. Later on, in the mid-20th century, engineers used the word bug to describe malfunctions with military gear. And if you're a science fiction aficionado like me, you might recognize the name Isaac Asimov, a very famous science fiction writer. In one of his early short stories, Catch the Rabbit, he describes a malfunction in a robot by using the word bug. Many of us are familiar with this early story in our industry. A group of engineers working in September 9th, 1947, on the Mark II computer in Harvard, under a software engineer, Grace Hopper, a Navy engineer, they found an error in the Mark II computer, and after analyzing, they actually discovered this moth that has entered into the machine. They logged it, and they logged it here at 3:45 p.m. And they indicated this is the first actual case of bug being found. This became a very known story. Grace Hopper went on to become a pioneer in the software industry, and they coined a lot of phrases we still use today. This story was an anecdotal that she frequently used, and that kind of became a story where a lot of people attribute it as the first case and where the word bug came from. Currently, this piece of paper is stored at the National Museum of American History in the Smithsonian Institute, and you're welcome to come and check it out. This is a neat piece of our industry history. And now we're going to explore a few cases of famous bugs that I found really fascinating. First, we're going to explore a case from the space industry. In the 90s, NASA has decided to send a mission to explore the Mars atmosphere and focus on getting more information about Mars climate. The mission was supposed to collect evidence of water distribution on Mars and evidence of past climate change. The mission launched in 1998. And in September 99, the spacecraft arrived at Mars. After completing a set of maneuvers, entering into the fifth maneuver into the Mars orbit, engineers from Earth were unable to contact the spacecraft. The day after, the spacecraft has been declared as lost, and no further communication attempts have been made. The reason for the failure was very simple. Lockheed Martin have been a subcontractor for this project, and when they built the thrusters for the spacecraft, they used the US-based measurement system. However, the specification they received from NASA and NASA building the ground station, they actually used the matrix system. That resulted in the thrusters being much powerful than they were supposed to be while performing the previous maneuvers. And it is assumed that the spacecraft was in a much lower altitude than it was supposed to be, causing it to incinerate in Mars' atmosphere. The results were that NASA lost about 4 years of research and development in exploring Mars' atmosphere. The total cost of the project was about $320 million that were lost. These are pictures of building the spacecraft, and all of that effort of 4 years have been lost, and basically we're more behind in our exploration of Mars than we could have been. The reason I wanted to talk about the specific bug, not the bug we see in the picture, is that although Lockheed Martin received the specification and used the wrong measurement units, it is very interesting to see that NASA itself, very early on, they actually did not put the blame on Lockheed Martin. They indicated, even in their earliest reports, that they placed the error on NASA itself. And this is something that they understand every software project, especially of this magnitude, will result in some kind of errors. But they expected their end-to-end testing and their testing procedures to indicate of this error. And they said that this kind of error should never made it to this late of a stage, not even to the launch stage. So obviously, more end-to-end testing procedures should have been observed, and they were able to correct their procedures based on that. The other part of it is that NASA acknowledged that there were some maneuvering engineers that indicated that they had concerns about the spacecraft altitude coming into the fifth maneuver. However, their concerns were largely ignored. And unfortunately, this was because due to wrong procedures when reporting the bugs, that bug and their concern. Obviously, reporting the bug, having proper procedures for it is important because that gives us the information to know how to reproduce it and which bugs should be placed on higher importance. However, in this case, where it can have such a large impact, we should have an ability to basically what's called break the ceiling and raise it to a higher level without going maybe through the standard procedure that we follow every day. In the second case, I still want to stay in the space agency. However, this was a mission that was constructed by the European Space Agency, the ESA. The mission was launching 4 satellites, and their scientific mission was to study the effect of solar radiation on Earth's magnetic field. Those cluster of 4 satellites was designed to be launched on top of the newly constructed ARIANE 5 missile. It was launched, and it was the very first mission for this missile. It was launched on June 4th, 1996. About 40 seconds into the launch, the onboard computer had noticed a very serious deviation off course, and it has initiated a self-destruct sequence. That self-destruct resulted in this very famous picture from this launch, and unfortunately, the entire spacecraft and the satellites on board were lost only 40 seconds into the launch. What basically happened? So this is, I believe, the only piece of code you'll see in this lecture. But what happened was a very unique set of circumstances. The newly constructed missile had on board a module called the Inertial Reference System. That piece of software was initially designed for the ARIANE 4 missile, but it was very reliable, and it was reused again on the ARIANE 5. Shortly before the actual launch, the procedure was halted, the countdown was halted and due to unrelated incident, and then it was resumed once it was corrected. However, if it was the previous rocket model, the Model 4, the countdown wouldn't have been able to be resumed so fast. But with the new hardware, it was. This subroutine in the module was never intended to be run during an actual launch. It was a diagnostic subroutine. But here, because the countdown was resumed so fast, this subroutine was actually running during the launch itself. Because of a different trajectory of this missile compared to other ones, this ADA code that was running had 7 variables, and one of them, this critical BH1, actually was trying to perform a 64-bit floating point integer number into a 16-bit signed integer. That caused an overflow, and due to some more series of events, it basically wrote the wrong value on the computer bus, and that caused the missile to go off course and basically self-destruct. So it was a series of very unfortunate events. Another piece of information here is that we have 7 variables here, but 4 of them were actually protected against this overflow. The one that was critical in this case wasn't protected against this due to some performance concerns that were raised during the initial development. What was the result of this? So the main result that I took is that the ESA, the European Space Agency, had a very reliable track record going into this launch. Their previous rocket modules were very reliable compared both to NASA and the Russian Space Agency. This launch, however, had a big impact on their reputation, and they had up until almost a decade afterwards, the Type 5 module was not as reliable as its previous ones. On top of that, losing those satellites has lost 370 million. It was a setback of, again, several years in that type of mission. However, there was one bright spot, actually, for this one. This was the first large-scale static code analysis that was ever performed. And those static code analysis tools are still being used today for us to improve our code quality going forward. And the reason I want to talk about this bug is that a lot of times, similar to this case, we're building a new system, a new application or a new system, and we're using, for example, a piece of a Python package that we used many times before. Very similar to how, in this case, a module that was used very reliably on the Type 4 missile was used again on the Type 5. However, obviously, the Type 5 missile had a very different mission profile and a very different trajectory. It wasn't applicable to use this module as is. And that's what I would encourage you to basically, each time that you're using a software package, a software module, you should pay attention to, is it, again, applicable in this case as it was? In most cases, it probably is. But obviously, here, more investigation engineering could have been done in order to avoid this mistake. And now we jump from the space industry over to talk about some phones. So this is Alexander Graham Bell placing the first call between, actually here in New York, to Chicago. And on January 15th, 1990, a lot of AT&T customers were trying to place long-distance calls. However, about half of AT&T's customers were unable to place long-distance calls that day. AT&T's engineers have been trying for about 9 hours to diagnose the problem. Initially, they assumed that they were being hacked by a malicious actor, and they engaged law enforcement to try to troubleshoot it, or to try to see if they can circumvent this malicious attack. However, the actual reason was much simpler than this. The AT&T was using a set of switches obviously for their long-distance calls. One of them, for example, here we see the 4 ESS switch. One of the switches in the network, actually here in New York, in Manhattan, diagnosed itself as being overwhelmed due to traffic. It reported to other switches that it is going offline and being taken out of the network. in the few months before this incident, actually, AT&T performed an update to the software. And while telling to the other switches that this switch is going offline, it has sent 2 notifications. However, what AT&T failed to recognize is that those 2 notifications to other switches will be coming too fast. And other switches that received the first notification were performing their own configuration update and reset. When they received the second notification, after only a millisecond, they assumed that to be basically an overwhelm of their system. And those switches diagnosed themselves as being malfunctioning. What you can probably see is that that caused a cascading effect throughout the system. And for the next 9 hours, all of the switches in the AT&T system were continuously rebooting themselves and trying to come back online without much help. The results were mainly financial losses for AT&T. They estimated about 60 million in lost revenue, 75 million unplaced calls, a huge brand and PR damages for them for having an outage lasting for 9 hours. They also invested in the previous years heavily building their brand as very reliable, and having this kind of incident was a big disaster for them. And the reason, what we can learn from this bug basically is that, again, a lot of time you might be doing some small update to a package or the set of code that you're currently working on. And in this case, AT&T, as I said, were very reliable. They tested various times this code update. And they were very certain it was fine. However, what they failed to take into account is this kind of how this would impact their entire switch network. They failed to take into account how the fact that they improved the reliability of just one switch and the fact that one switch will be able to be reset much faster. They failed to take into account that this will have a side effect and would basically, once one switch goes down, it would have the side effect of bringing the whole network down. And from that, we'll move to a next bug. This is not the only case, but this is one of the famous cases recorded of software bugs actually causing fatalities. The Patriot system has been used by the US Army all the way going back to the 1960s. During the 1990s, the US Army has deployed Patriot defense systems in the Middle East in order to defend the US forces and allies against what was expected to be, during the first Gulf War, Scud missiles fired at them. This was the first time that those systems were supposed to be used to combat Scud missiles. However, on February 25th, 1991, the Patriot system defending the Dhahran Air Base in Saudi Arabia detected an incoming Scud missile, but failed to intercept it. The reason was that in order to understand, we need to understand a little bit how the system works. Basically, the system detects the missile, and then it needs to calculate the trajectory of the incoming missile in order to intercept it. However, what happened is that when calculating the radar results from the incoming missile, it needed to convert the timestamp. And there was precision that is there was a loss of precision on converting that timestamp. And actually, the funny part is that engineers designing the system understood that, and they built a subroutine in order to basically deal with that challenge. However, there were 2 places of that conversion being done in the system, and they have only applied that conversion, the right conversion, in one of them. That resulted in a drift in the system between the 2 system clocks, and it resulted in a proportional error as the system was continuously running. So here you can see the system that maybe just came online. It can perfectly track the missile. However, here at the far right, you can see a system that was working for about 20 hours, and it would completely fail to track the missile. And so basically, as the system was running more time, it was becoming useless more and more. As I said, the results of that were fatal. The incoming Scud missile has made a direct hit on the barracks in the base. 28 soldiers were killed and 110 injured. Most of them were reserve duty personnel from Pennsylvania. And basically, the reason I want to talk about this bug is a little bit of background for this. The issue actually was reported by Israeli operators about 2 weeks before to the Patriot system project back in the US. However, the project engineers have assumed that this was an outlier and the system wasn't actually being used correctly. They assumed that no one will be using the system continuously for this long. This was obviously a big gap between how the engineers actually assumed the system to be used and how it was actually being used in the field. And this is something that I feel that happens to us a lot, where we develop a system, we're deep into the code, even if we have some broad picture, but we fail to see how the system would actually be used by the actual customers and by the actual users. Another problem was that a few days after, the project office actually decided that this might be an issue, but they decided that they're going to they will issue an alert saying that the system should be restarted, but they didn't indicate how long it would take. So I want to do one more bug, but I think we're coming a little bit on time, so I'll run through it real fast. Basically, this is you might recognize this movie. It is The War Games from 1983. It was basically a few months afterwards, the early detection system in Russia trying to detect incoming nuclear missiles has alerted of 5 incoming nuclear launches from the US. The high-ranking officer in that incident have analyzed the data and decided that all of these are false alarms and prevented from initiating a second strike capability by Russia towards the US, by that basically preventing a nuclear war that might have happened in 1983. This has happened due to a unique set of circumstances where basically there was a sun glare going back from the sun to the Russian satellite and causing that false alarm. So with that, that was real fast about the last bug, but I wanted to jump in and kind of, in conclusion, you might have come here expecting maybe an ideas about how not to create famous bugs. Unfortunately, I can't give you that. I hope you did learn about some ideas about what you should be doing, what we all should be doing better. Maybe some more end-to-end testing, catching more edge cases as the systems that you are working on are much more critical. And I think it is a unique possibility as you're learning from these reports online and that are widely available. So if you found this interesting, I encourage you to go and learn some more. I had a lot of fun preparing this talk. If you have any questions, I'll be out in the hall. Very happy to answer. Thank you very much. Appreciate it.